All right, so the last part we're going to do on determinants is how can we use elementary row operations to compute a determinant. So let's remember the elementary row operations. So elementary row operation 1 would be just exchanging rows. Now, if A and B are related through row operation of the first type, say A or B is obtained from A by performing an elementary row operation of the type 1. You exchange two rows, whatever it may be. Then what we have is that the determinant of A is going to be equal to the negative of the determinant of B. Ooh, I almost gave myself no room there. So if you perform throughout your row operations, and when I do row operations to simplify the matrix, our goal, maybe I should have talked about the goal first, is to change our matrix A, whatever it may be, and change it into a diagonal matrix. Let's call it maybe we'll call it B. B11, not diagonal, B upper triangular is sufficient. So B22 to B2n. And maybe some stuff here we don't care about, and then zeros down here. That's going to be our goal. Why? Because the determinant of such matrix I should say 2n, B and n. It's like a news channel, but not. So if you have a matrix of this form, the option of that is that the determinant would be the product of the diagonal entries. So if I can perform operations and I can control what happens to the determinant through those operations, and then I can get it to not a reduced row echelon form, but down to an upper triangular, which is shorter, then I can compute the determinant really easily. This is much faster than actually doing cofactor expansions if you're doing it by hand. So let's take a look at how our elementary row operations affect the determinant. So elementary row operation of type 2, let's say that is going to be adding a multiple of a row to another. Multiple, I guess, of a row to another. Let's leave it at that. So if you obtain A, or B rather, from A by performing an elementary row operation of the second type, and my numbering may be completely off from the book or my notes or whatever, doesn't matter, the determinants are the same. So this type of operation does not affect the determinant at all. That's awesome. Because if I perform these operations, I can perform as many as I want of those, and then my determinant is not affected. I recommend just using these two types of operations, because then the only thing you have to do is keep track of how many exchanges of rows you did, and then you just multiply -1 to that power of however many times you exchange the rows. So you just have to look for negatives. The next elementary row operation, which is multiplying a row times a non-zero constant, it does affect the determinant. So unfortunately, this one can lead to mistakes. So I recommend not to do it, but I'll also show you how to deal with it if you really, really have to. And when do you really, really have to? Never. It's just because you like to. So here is multiplying a row times a non-zero constant k. What that's going to do is the determinant of, oh, I should have written that I'm going to perform the operation on whom. So let's erase this. So A, you're going to obtain B from A by performing an elementary row operation of the third type. So you're going to be multiplying a row of A times some constant k. So the determinant of B now is going to be k times the determinant of A. But usually you want to find the determinant of your original matrix. So you want to find the determinant of A. So it's better to write the determinant of A as 1 over k is non-zero, so you can get away with that. Determinant of B, I'm writing really small because I ran a space there. So what happens is that if you're going to multiply a row times a scalar, whenever you're going to compute your determinant of A at the end, you get to divide by that scalar. So I don't like that because then you forget whether you want to multiply or you have to divide by it. So I recommend you just do the first two elementary row operations, but it's your problem, not my problem, so you choose however you do it. So let me show you a quick example how to use it. And I'm going to first compute it without using the elementary row operations of the third type, and then we'll do one with the elementary row operations with the third type included. All right, so let me erase. I'll be right back. All right, so here's the example. So let's say we have this matrix and we want to compute the determinant. Now this one again, if you were to do cofactor expansion, you have this row right there that is quite nice. Then you would go ahead and do what we did in the previous example. That took a little bit of time, but it was not prohibitive, but not terrible. But this is how you do it. You perform with row operations. So you perform a few row operations, and preferably of type 2 or type 1. So I'm going to do a bunch of type 2. I'm going to say row 2 minus row 1. I just do this minus this. That eliminates this 1, starting to move it into an upper triangular type. Then I'm going to do row 3 minus 2 row 1. Again, eliminating that one. And this one right here, I'll do also row 4 minus 3 row 1. So when I do all those operations, so copy the first one. You're going to subtract, so this minus this, 0. This minus this, 0. 2 minus 0, 2. 3 minus 1, 2. Now I'm going to do this minus 2 times this. So I'm going to get 0 here. 1 minus 2 times 2 is going to be negative 3. So it's going to be 1 minus 4. 1 minus 0 is 1. And then 1 minus 1 is 0. Ooh, I was going to write 1. That can ruin your problem right there. So thankfully we didn't make that mistake. So this is going to give me 3 minus 3 is 0. 0 minus 3 times 2, negative 6. 0 minus 0, 0. And then 1 minus 3 is going to be negative 2. Now, it seems that this row should already be below, so I'm going to exchange rows. And that is going to make me pay with a negative number. So row 2 and row 3 I'm going to exchange. And I'm going to make a big note here that I'm going to pay with a negative 1. My determinant, the beauty of negative 1 is that I don't have to divide or multiply. It's the same thing. So I'm going to remind myself I need to multiply times negative 1 when I'm done. Please do that. So I'm going to exchange those two rows. So I'm going to have 1, 2, 0, 1, 0, negative 3, 1, 0. And then 0, 0, 2, 2. And then the last one we leave alone. Oh, that matrix got a little bit out of out of view, but this is a negative 2. But I know you're following me along and writing on your notebook, so you got the same answer, right? All right, one can always hope. So right here, what I'm going to do to avoid, normally what you would do, let me tell you what you would do. You would divide this by negative 3 to make that a 1 in your pivot position. But you're not going to do that because now you're computing determinants. You're not going after the reduced row echelon form. So what you're going to do, you're going to say, well, I can grab row 4 and I'm going to subtract 2 times row 2. You see, then you get this minus this is going to be 0, and then you're going to end up with this position being 0, and you're going to eliminate all the non-zero entries below the pivot. Did we change it to the pivot to a 1? No, but you don't have to because you're computing a determinant. So now I'm going to copy my matrix here, this as well. And now I'm going to copy as well. Copy everything. And now I'm going to subtract. So I'm going to have 0. This right here is 6 minus 2 times 3 is going to be plus 6. So it's going to be 0. This minus 2, negative 2. And then negative 2 minus 0, negative 2. Oh my goodness, I got a matrix whose determinant is 0. A singular matrix. Good job, man. Anyway, it doesn't matter. It is what it is. So the last thing I'm going to do is say row 4 plus row 3. And then you just get the matrix. And then when you do that, and then your determinant is the product of the diagonal entries times -1, right? Because I did have a -1 going along for the ride here. So, but the determinant then of A from all this, I'm going to squeeze it right here. Determinant of A would be determinant of this matrix, which is 0, times -1. Well, still 0. And that is how you use elementary row operations to compute the determinant. All right, guys, so I ran out of time again, and but I think that gives you a good idea how to solve problems using elementary row operations to compute the determinant. So we'll leave it at that. And if you need another example, please do let me know in the comments. But I think the explanation is good. I think it's clear. So thank you for watching, and I'll see you in the next one.